Okay, hello everybody. I'm Beck and I'm a postdoc at the Observatory of Munich. And I will give, I think, the only talk about magnetic fields and galaxies here. So you will hear the word magnetic field a lot during my talk, probably more than in all the other talks combined. Why should we mess about with the magnetic field, or why do I work on it? Well, because it's simply observed. So we see synchrotron radiation from external galaxies, and wherever we observe synchrotron radiation, magnetic fields are present. So here the synchrotron radiation follows a nice spiral structure as well, with varying intensity of M51. Or for example, in this galaxy, there's a nice synchrotron halo around the galaxy. In this galaxy here, there's outflows or something observed, or at least something which causes synchrotron radiation here. In the Andromeda galaxy, it has a nice pattern and also ordered field lines. So, how do we describe magnetic fields? I work with simulations. So, the main equation here is the induction equation of magnetohydrodynamics. And if you look at the equation at the front part, you know that one problem I want to tell you already about. If you put an initial value of 0 here in the front part of the equation, you will not evolve a magnetic field in time at all. It will remain 0 forever. Which means that you might need to add some kind of seeding term at the equation which injects magnetic fields, which then later on can be evolved by the front part. And here everything, what happens to the magnetic fields, comes from velocity motions. Here are some topological changes like diffusion or ordering in space. And for simulations, you need to use this equation and solve it in the context of the galaxy, which leads to two questions. Okay, you have the process of galaxy formation here, and you have the magnetic fields there, so you can ask two questions. First of all, how does galaxy formation affect the magnetic field growth in the galaxy? And the second one is, what might the magnetic fields do to the formation of the galaxy? The second question, I have no idea. The first question I will address in this talk. Okay, so here, also something interesting. Did the first generation of galaxies or stars form in magnetized or in unmagnetized gas? So what caused their C fields, for example, or the later transport around the galaxy? Very inspiring paper here from the 90s by Russell Kalsford, who suggested a protogalactic origin for the magnetic field. So he was one of the first to do the model of, okay, why the galaxy forms. The magnetic C field is created, it's amplified, and later on distributed in the whole galaxy. And this is also the message that galactic magnetic fields are a result of the galaxy formation process. So if you take any message from my talk, please take this message, that whatever magnetic field you observe in the galaxy was created while the galaxy was formed. Okay, so now in my simulations I use something called a stellar origin model for the magnetic field. So this means that I start without 0 magnetic field at the beginning, and wherever in the simulation star formation is taking place, I will inject magnetic fields at that position, which is something like a supernova or stellar origin scenario. This means that the term at the last end here needs to be modeled continuously in the simulation. So you follow the amount of supernova, you can calculate how much magnetic field would be injected here. And this approach is advantage to the one where you usually start with an initial value, because then it gives you some kind of constraint on the local and on the time injection of the magnetic field. On the other hand, this is cosmological simulation with gadget, and this approach is also very dirty from the numerical side of view. Okay, so now we follow the simulation of the Milky Way-like galactic halo. So here, don't expect a nice galactic disk or anything, but just look at the halo and we will analyze the magnetic field. So while the halo is forming here, you see the very radius, you see dense clumps, star formation is taking place, and everything is evolving in time. Simulations here have been performed with gadget, and they use very simple prescriptions for cooling and feedback. In that case, the standard model by Springer and Hernquist here, we do not follow metallicity or black hole evolution yet in these simulations, because it's simply too complicated from a numerical point of view yet here. Now, if we look at the magnetic field closely, because that's what we're interested, is that while here you see black, no magnetic field is present at the beginning at all. It starts to appear at the small dense gas clumps, which we saw before, where also kind of cooling and star formation is taking place. So wherever here are supernova going off, I will inject in the simulation a magnetic field at these positions, and And then I can simply follow the evolution of those clumps as they fall into the central object. Around redshift 4 and 2, very high field strengths are reached in the simulation, which are then relaxing towards redshift 0. So here this might correspond to the very messy stage of galaxy formation and evolution at redshift 2 here, which also causes like a lot of high field strength. And then everything's relaxing to the end. Now, for one observable quantity, we can look at the Faraday rotation measure, for example, which is the integrated line of sight between electron density and magnetic field, so it's still a combination of both. But we calculated this for the same halo as before, and we found that, for example, we have very, very high Faraday rotation measures, so up to 1000 in dense objects, or in these clumps here. Then we can follow also the evolution in time, for example, here at redshift 2. The distribution is also extremely patchy. So now imagine if somebody takes an observational sideline through the halo here, it will be contaminated by whatever is present in the gas between the galaxies or the clumps here, as well as coming from the main object. While towards redshift 0, the situation is more relaxing, and the Faraday rotation measures have declined to something of the order of 10. Okay, now we can also look this a little bit across redshift. Here is the redshift evolution from 4 to 0. And the colors show you the mean Faraday rotation measure in the simulation, and overlaid are some first data points just collected from the literature. But this comparison has also been taken very carefully because the observations are just individual sightlines, while in the simulation I've taken a mean of several sightlines, and also the environment needs to be respected if the observed light of sight was for a cluster medium or for an isolated galaxy. This might change the order of magnitude here as well. But whatever we find first hints that the trend towards very high rotation measures here of about 1000 and towards redshift 0 of order of 10 might be reproduced by our simulation, and this is also verified by the histogram of Faraday rotation measure. Okay, so the magnetic field growth very quickly. Now here's a run with a primordial seed field, so just for control running I put spatially constant seed field everywhere, and then I just checked how the mean value of that within the halo is evolving in time. And we see, okay, here somewhere comes the seed field level in, then is a phase of rapid amplification of the magnetic field. This was also what we saw on the contour plot before, where the magnetic field strength goes up very, very high, and then between redshift 4 and 2 here, it has reached the maximum, which we also saw before, and then it's a site of decay here. So these different phases like seeding, amplification, and then some kind of maybe bordering. And the amplification here is caused by dynamo processes of all kinds. Now, simulations are nice, but we also need to kind of understand what is happening in the simulation. So analytical toy modeling is always very nice to have. And here we have tried to kind of understand a little bit what's going on in the simulation to get an idea if this what we found is okay or coincidental or not. So I say yes, it is. We've kind of used the toy model here that the growth of the field can be described by the growth of some perturbations within a turbulent flow. And this leads to an equation here of the growth of the magnetic energy with some kind of growth factor where we then put in, okay, growth stops, it saturates at some point, where we set the equipartition between magnetic and turbulent energy is reached. So here this is the saturation level. We're taking some growth rate, which was estimated from turbulent motions. And this leads us to an equation at the end, which when we're solving this here, which we can compare to the simulation. And okay, we did several degree levels, we plotted a toy model and different simulations, and we found some kind of agreement between them. And this convinces us that this, what we saw before in the simulation, is okay, and we can trust it a little bit. Okay, there has been similar work afterwards as well by me with different numerical methods. And here, for example, I want to also say one paper from a grid code. So I showed gadget results, and there's also grid codes results, very nice one here, by Romain, where he also showed that the amplification is also driven by the size of the resolution, and also it matters if the simulation includes feedback or not. So with feedback you achieve higher growth rates and higher field strengths as well here. So this is also convincing that we might kind of have understood a little bit how the magnetic field in the galaxy is growing during the galaxy formation process. And here just summarizing and concluding that I would like to hope in the future that the communities of galaxy formation and radio astronomy maybe have a little bit more overlap, and that also I see more magnetic field investors at this kind of conferences, and maybe more galaxy formation people at the other kind of conferences, because that might benefit both sides here. And in the end, the second question is, okay, the magnetic field or related non-thermal processes, like we heard in the radio talk with cosmic rays, have yet to be investigated, and let's see what the impact will be.
Thank you.